Hello NAE students, welcome to the heat transfer laboratory. In this lab session, we are going to conduct the experiment on determination of thermal conductivity of an insulating powder. The objective of this experiment is to determine the thermal conductivity of an asbestos powder. First, let's have the look at the experimental setup. In this experimental setup, this is the main switch used to provide the electricity to the heater. This is the voltage indicator. This is the current indicator. And this is the temperature indicator. This one is dimmer start, which is used to provide the required voltage and current to the electrical heater. And this is the test chamber. Now let's have a look at the test chamber shape. So this test chamber is going to be like a sphere. Okay, so in this test chamber there will be two concentric spheres. So there will be two concentric spheres, and the inner sphere, the outer sphere will have diameter of 250 mm, while the inner sphere will have diameter of 60 mm. And the gap between these two spheres, which are made with steel, is filled with asbestos powder. And the inner surface of the inner sphere will be brought in contact with the electrical heater. When the inner surface of the inner sphere is heated, the temperature heat is going to be conducted from inner surface to the outer sphere through the asbestos powder, because of which temperature of the surfaces will be changed. This change in surface temperature will be measured with the help of 12 thermocouples. Out of 12 thermocouples, 6 thermocouples will be mounted on the inner sphere. That is thermocouple number 1 to thermocouple 6 will be on the inner sphere, while thermocouple number 7 to thermocouple number 12 will be mounted on the outer sphere. So the average of first 6 thermocouples, that is the average of temperatures from T1 to T6, will give us the inner surface temperature of the inner sphere, while the average of temperatures from T7 to T12 will give us the surface temperature of the outer sphere. So there is going to be two concentric spheres. Inner surface of the inner sphere is assumed to be at a temperature of Ti, which is going to be the average of first 6 thermocouple readings. Then the outer surface of the outer sphere will be at a temperature of T0, which will be equal to the average of temperature from T7 to T12. And when since Ti is going to be greater than T0, that is since inner surface will be in contact with the heater, Ti will be always greater than the T0. So because of the temperature difference between the inner sphere and the outer sphere, the heat will be conducted through the asbestos powder by the conduction mode. Once the energy reaches the outer surface, T0 is going to be greater than the surrounding air temperature, T infinity. Okay, because of the temperature difference between outer sphere and the air surrounding it, that is when the air is at T infinity temperature, when T0 will be greater than T infinity, from the outer surface heat will be transferred to the still air, by convection mode as well as by the radiation mode. Therefore, when system attains the steady state, okay, we can say that heat conducting through the asbestos powder, which is filled between the two concentric spheres, should be equal to the heat convecting from the outer sphere plus heat radiating from the outer sphere to the surrounding air. Under steady state condition, therefore, we can say that heat conducted should be equal to heat convected plus heat radiated. Now we can go for finding the heat conducted through the hollow sphere according to this expression, Q conduction equal to delta T by R sphere. Here R stands for the thermal resistance of the hollow sphere. Okay. where Ti and T naught actually stands for inner surface temperature and the outer surface temperature of the spheres, while K represents the thermal conductivity of the asbestos powder, and Ri and R naught represents the inner radius of the sphere. Okay, it is the radius of the inner sphere, and R naught is the radius of the outer sphere. Heat convected from outer sphere can be calculated according to Newton's law of cooling, according to which Q convection will be equal to heat transfer coefficient into area exposed to the air into temperature difference between the surface and the air. Okay, that is H into A naught into T naught minus T infinity. Heat radiated from the outer sphere can be calculated from Stefan-Boltzmann law of radiation, according to which Q radiation equal to sigma into A into epsilon into Ts to the power of 4 minus T infinity to the power of 4. So therefore, when the system attains a steady state, we can go for substituting all these heat transfer expressions in the above equation, and we can go for determining the unknown thermal conductivity of the asbestos powder. So in this particular equation, except K, all the temperature values will be taken during the experimentation when the system attains a steady state, and areas will be known to us because of the geometrical specifications. Okay, and hence we can easily find the thermal conductivity. But only thing is we need to find out the heat transfer coefficient H theoretically based on the dimension numbers that we will see when we take up the calculation part. So before we proceed for the conduction of the experiment, we need to make the following observations with respect to this experiment. So insulating material used here is asbestos powder, and sphere material is steel, and diameter of inner sphere is 60 mm, diameter of outer sphere is 250 mm, and room temperature is 30 degrees centigrade. This room temperature will be noted with the help of thermometer. Now it's the time for conducting the experiment. Before we proceed for the conduction of experiment, we need to understand the procedure. So we have to turn on the power supply, and then we have to adjust the dimmer start to set the required heat input by setting the voltage and current. Then we have to wait for the system to attain the steady state. It will take around 40 to 50 minutes time for the system to attain the steady state. Once the system attains the steady state, we have to note on the thermocouple readings from T1 to T12. So thermocouples from T1 to T6 will be on the inner sphere. Thermocouples from T7 to T12 will be on the outer sphere. Then we can go for repeating the experiment with the different heat inputs. So this is the experimental setup for determining the thermal conductivity of the insulating powder. So this is the test chamber which will be in the form of sphere. So there will be two concentric spheres. Only we can see the outer sphere, but inside this there is going to be one more inner sphere. The gap between the inner sphere and outer sphere will be filled with the insulating material, that is asbestos powder. And you can see also the thermocouples mounted on the outer sphere, and you can see there are two wires, thermocouple wires, which are going here. So another wire will be coming in contact with the inner sphere. So this is the main switch which will supply the electricity to the heater, and this is the dimmer start which will be used to set the voltage and the current to the electrical heater. So this is the voltage indicator and this is the current indicator, and 12 thermocouple readings can be checked by turning the temperature knob here. So this is the temperature indicator. So here it is written that outer radius is 0.125 meter and inner radius is 0.03 meter. The meaning is that inner diameter is 60 mm and outer diameter is 250 mm. And here also it is mentioned thermocouple 1 to 6 indicates the inner surface temperature, and channel number 7 to 12 indicates the outer surface temperature. Now we are going to turn on the instrument. So main switch will be turned on, and you can see initially voltage and current are 0. Then we are going to turn the dimmer start in the clockwise direction, and we are going to increase the voltage and current for the required value. We have set voltage to around 40 volts for this demonstration or for the first trial. So voltage applied is 40 volts and current passing through the electrical heater is 1.41 amps. Now you can see the temperature thermocouple 1 reading in the temperature indicator. Right now T1 is 25 degrees centigrade, which indicates the temperature of the inner sphere. T2 is also at 24 degrees centigrade. T3 is at 24 degrees centigrade. Now T4 is at 25 degrees centigrade. T5 is at 25 degrees centigrade. And T6 is also at 25 degrees centigrade. So first the average of first 6 thermocouples will tell us about the inner sphere temperature. Then T7 is also at 25, T8 is also at 25, T9 is also at 26 degrees centigrade. Then T10 is 25, T11 is at 26 and T12 is at 26 degrees centigrade. So this clearly indicates that when we start the experiment, all the thermocouples are showing the same temperature of around 25 degrees centigrade. Okay. Which represents the initial temperature of the spheres. After 20 minutes, so you need to remember that for every 5 minutes you should go for noting the temperatures of the thermocouples. And after 20 minutes you can see we have maintained the same voltage and current to the electrical heater. And you can notice here the temperature T1 has increased. Initially it was 25 degrees centigrade, now it is increased to 61 degrees centigrade. You can go for checking the thermocouple 2 reading now by turning the temperature indicator knob. So temperature indicator knob will be turned in the clockwise direction, and we can go for checking the T2 temperature, then T3, then T4, then T5. So it is showing that all first 6 thermocouples are showing temperature of around 60 degrees centigrade, which corresponds to the surface temperature of the inner sphere. Then T7 is around 34, T8 is also around 34, T9 is 27, T10 is 35, T11 is 33, T12 is 35. So approximately the outer sphere is at a temperature of 34 degrees centigrade. Okay, so we will wait for a few more minutes for the system to attain the steady state. After steady state is reached, that is after 45 minutes. Okay, now the question is how to judge that the system is attained steady state or not. So you should go for recording the temperature of the inner sphere and outer sphere for every 5 minutes interval. Okay, the moment when you are going to notice the temperature at some time are same as previous temperatures, okay, then we can say that the system has attained the steady state. Okay, so in this case when we noted the temperature at 45th minute, okay, those temperatures, those recorded temperatures were exactly same as temperatures obtained at 40th minute. Therefore we concluded that the system has attained the steady state, and hence we recorded the steady state temperatures. Now you can see after 45 minutes still we have maintained the voltage and current to the electrical heater as same. It is around 41 volts and current is around 1.45 amps. Okay, so T1 temperature is 75 degrees centigrade when the system attained the steady state. Okay, now we can go for noting the remaining thermocouple readings by turning this temperature indicator knob. So T2 is 75, T3 is 74, T4 is 74, T5 is 74, T6 is 75, T7 is 39, T8 is 39, T9 is 29, T10 is 39, T11 is 36, T12 is 39. We have to note down these 12 thermocouple readings when the system attains the steady state. Then we have to turn the dimmer start in the reverse direction, and we have to bring the voltage and current to 0. It should be turned in the counterclockwise direction and bring the voltage and current to 0, and then turn off the main switch. This completes the conduction of the experiment. Now it's the time for filling up the tabular column. First we have to note down the voltage and current supplied to the electrical heater. So in this trial we had given voltage of 41 volts and current of 1.45 amps, which represented the heat input of 59.45 watts to the electrical heater. Okay. And when the system attained the steady state, the following temperatures were recorded. That is, T1 is 75, T2 is 75, T3 is 74, T4 is 74, T5 is 74, T6 is 75, T7 is 39, T8 is 38, T9 is 29, T10 is 39, T11 is 36, T12 is 39. Okay, so these are the temperatures recorded when the system attained the steady state. Okay, and also you need to remember that the ambient temperature was 30 degrees centigrade, which was measured with help of thermometer. Now it's the time for doing the calculations. So we are going to find out the conductivity of the insulating powder with the help of steady state condition, that is heat conducting through the sphere should be equal to the heat convecting from the outer sphere plus heat radiating from the outer sphere. So for that steady state equation to be used, first we have to calculate the heat conduction occurring through the hollow sphere. So in order to find the heat conducting through the hollow sphere, first we have to find out what is the inner sphere temperature and outer sphere temperature by taking the average of first 6 thermocouple readings. Okay, when we take the average of first 6 thermocouple readings, we will get Ti, and when we take the average of thermocouple number 7 to thermocouple 12 readings, we are going to get the outer sphere temperature. So in this case we noticed that Ti is 75 degrees centigrade and T0 is 38 degrees centigrade. That is, the inner surface is maintained at temperature of 75 degrees centigrade, and the outer sphere is maintained at temperature of 38 degrees centigrade when system attained the steady state. And because of this temperature difference across the inner surface and the outer surface of the hollow sphere, okay, so heat is going to be conducted, and that heat conducted can be calculated according to this expression delta T by R sphere, and this R stands for the thermal resistance offered by the hollow sphere. Okay, but in this case this hollow sphere has been filled with, so the gap between the two spheres has been filled with insulating material. Therefore, when the heat tries to conduct from inner surface to the outer surface or the outer sphere, okay, so the asbestos powder which is present between the two spheres will offer the resistance. That resistance offered by the asbestos powder, which will be in the form of hollow sphere, can be calculated according to this equation 1 over 4 pi k multiplied by 1 over Ri minus 1 over R naught. This you can take it from the thermal data handbook. Okay, and Ti and T naught corresponds to the inner sphere temperature and the outer sphere temperature. Okay, after substitution and in this expression you need to remember the thermal conductivity of the asbestos material is unknown. That only we are trying to measure. So after substitution we can go for expressing the heat conducting through the asbestos powder in terms of the thermal and in terms of its thermal conductivity. Okay, so here we have got it as 18.35 K. Then we can go for determining the heat that is convecting from the outer sphere to the surrounding air. So we know that outer sphere is at a temperature of 38 degrees centigrade, and it is exposed to the still air which is at a temperature of 30 degrees centigrade. Okay, during the because of temperature difference between the outer sphere and the still layer, okay, the convection can occur. Okay, and this convection, in order to find the convection, we have to use the Newton's law of cooling, for which we require the heat transfer coefficient value. In order to find the heat transfer coefficient value, we are going to find out the film temperature. So film temperature is nothing but it is the temperature of thin layer of air which will be in contact with the outer sphere. Okay, so this film temperature, or the temperature of the air which will be in contact with the outer sphere, can be taken as the average of outer sphere temperature and the ambient temperature. So when we take that, we got the film temperature as 34 degrees centigrade. Then we are going to, as we know, the properties of fluids are going to change with the temperature and pressure. Therefore, we are going to note down the properties of this still air at 34 degrees centigrade for sake of easy simplification. Okay. We are going to take 34 degrees centigrade as approximately 35 degrees centigrade, so that we can take the properties easily from the thermal data handbook. Okay, so therefore these are the properties that we will be interested in for the calculation purpose. We are going to note down the kinematic viscosity, Prandtl number, thermal conductivity, and the coefficient of volumetric expansion, that okay, from the thermal data handbook. Okay, so here you can see the properties of air. You can see the properties of air given for different temperatures. Okay, and we are interested in knowing the property of air at 35 degrees centigrade. So but in the data handbook only properties are available at 30 degrees centigrade or 40 degrees centigrade. Therefore by taking the average of property at 30 degree and 40 degree, we can get the corresponding properties for 35 degrees centigrade. So we are going to note down the kinematic viscosity, we are going to note down the Prandtl number and thermal conductivity, okay, for the air at 35 degrees centigrade. Then we are going to calculate the dimension numbers. For natural convection, the governing number will be the Grashof number. This Grashof number will be calculated according to the equation G into beta into delta T into L cube by nu square. Okay, so for free convection over the sphere, the characteristic length will be taken as the diameter of the sphere, which will be 250 mm for this experiment. Okay, and the temperature difference between sphere and the air will be T0 minus T infinity, which will be 8 degrees centigrade here. So by substituting this characteristic length as the diameter and the temperature difference as 8 degrees centigrade, and by substituting all the properties that we have taken from the data handbook in this Grashof equation, Grashof number equation, we got the Grashof number as 14.67 into 10 power of 6, and then we are going to multiply this Grashof number with the Prandtl number. The product of Grashof number and Prandtl number will be called as the Rayleigh number, which we are getting here as 10.05 into 10 power of 6. Now, okay, based on this product of GR and PR, okay, so in this case our calculated GR and PR is coming in between 3 into 10 power of 5 and 8 into 10 power of 8. So therefore so for this range of GR PR, we can take the Nusselt number correlation from the thermal data handbook, which will be like Nusselt number equal to 2 plus 0.5 times GR PR to the power of 0.25. So we are going to substitute the value of the Rayleigh's number here, that is the product of GR and PR will be substituted here. Okay, and based on that we are going to get the Nusselt's number as 30.15. We also know that Nusselt's number is nothing but it is HL by K. Okay, this is the general expression for Nusselt's number. Okay, but here a characteristic length is the outside diameter of the sphere. So therefore by replacing L with D naught, we can go for finding the heat transfer coefficient. So so we have substituted the Nusselt's number here, then conductivity of the air at 35 degrees centigrade we have substituted, and outside diameter of the sphere is substituted here. So based on that, we got the theoretical heat transfer coefficient as 3.275 watt per meter square Kelvin. Once we find the heat transfer coefficient, next step is to calculate the heat convecting from the outer sphere to the still layer by using the Newton's law of cooling. So we have substituted the H value here. Okay, so we have substituted the H value here, and this A stands for the lateral surface area of the outer sphere, which will be equal to 4 times pi r square, that is r naught square here, outer radius. So based on that, we calculated the lateral surface area of the outer sphere, which is 0.196 meter square. That has been substituted in the Newton's law of cooling equation, and the temperature difference is actually 8 degrees centigrade between the outer sphere and the still layer. Okay, so based on these substituted values, we have got the rate at which it is transferring to the from sphere to the air by convection mode as 5.135 watts. Then we will go for determining what is the rate at which it is going to the still layer by radiation mode from the outer surface. Okay, so we know that outer surface is at a temperature of 38 degrees centigrade, air is present at 30 degrees centigrade, that is the ambient temperature or room temperature. Okay, so now radiation can also occur between the outer sphere and the still layer. So in order to find this heat exchange between the outer sphere and the still layer by radiation mode, we are going to make use of Stefan-Boltzmann law of radiation, okay, which is given here. Okay, and here sigma stands for Stefan-Boltzmann constant, which will be 5.67 into 10 power of minus 8 watt per meter square Kelvin to the power of 4. A stands for the lateral surface area of the outer sphere, and epsilon stands for the emissivity of the sphere material. Okay, and Ts and Ts represents the outer surface outer sphere temperature, and T infinity stands for the ambient temperature. So by substituting the sigma value and the lateral surface area value and the emissivity, so here this is very important. Emissivity of the steel surface under polished condition has been taken here, okay, because the sphere is made with steel and the steel is polished. Okay, so it is in the polished condition, therefore the polished surfaces will emit lower radiation, so it has been taken and it has been assumed as 0.1, okay, as per the data handbook. So therefore and Ts and T infinity should be substituted in Kelvin. So we have converted temperatures from degree centigrade to Kelvin here. Okay, and after substituting all this temperature, area and the emissivity and the Stefan-Boltzmann constant in this Stefan-Boltzmann equation, we have got the radiation heat transfer between the outer sphere and the air as 1.03 watts. Okay, once we determine this radiation heat transfer rate, then we know that for under a steady state heat transfer process, always heat conducting through the sphere should be equal to heat convecting and heat radiating from the outer sphere to the surrounding air. So by substituting all these conduction heat transfer values, convection heat transfer values and radiation heat transfer values, okay, we will see that only unknown here is conductivity of the asbestos material. So on simplification, we will get this conductivity as 0.3186 watt per meter Kelvin. So we can write the result as thermal conductivity of asbestos powder is 0.3186 watt per meter Kelvin. Now this experiment can be repeated by providing a different heat input to the inner sphere. So you can give different voltage and current to the electrical heater which is in contact with the inner sphere, and you can go for knowing the effect of heat input onto the conductivity of the insulating material, because as we go for providing more heat input, okay, for the inner sphere, the temperature of the insulating material is going to be increased. So what is going to be the effect of temperature on the thermal conductivity can be known by repeating the experiment at different heat inputs. So this completes the experiment on determination of thermal conductivity of an insulating material. Thank you.